Well, Assalamu alaikum everybody. Dear students, we are meeting you again in another lecture. It is lecture number 9, actually on vector calculus. This is 9th lecture on vector calculus. We have already delivered the lecture number 8 on vector calculus, where we are starting this vector integration. We have introduced what is vector integration and some applications we did there. Now I am again trying to share with you some more applications on this vector integration. Then afterwards we will go to line integral and the application of line integral, the physical representation of line integral, that will come later. Let us see how we solve such questions. Sometimes we have to find out r cross d2 r by dt square dt, such questions when r of t is given by this. Sometimes r dot dr by dt, so on and so on. This is in this question we are finding out the cross product of this with respect to t. It is a definite integral from 1 to 2. Let me see how we solve such question. You see, if we go to the solution of this, please, before going to this lecture number 9, you should go through the lecture number 8, where we discussed all these things. dr cross dr. I will again write this. We have if we find out derivative of r cross dr by dt with respect to t, what is this? It is dr by dt cross dr by dt, then plus, I am using the cross product for differentiation. This is r as it is, cross derivative of this, it is d2 r by dt square. Now this is 0, cross product of a vector with itself. So that means you are getting derivative of r cross dr by dt with respect to t is given by what? It is r cross d2r by dt square. We had proved this result in previous lecture, but I am again touching this here. You see, when this is this, by the reverse process of integration, we can write that this implies integral of r cross d2r by dt square with respect to t is simply r cross dr by dt, as by this, because derivative of this is this, that means integral of this with respect to this the integral coefficient of this is r cross dr by dt. Now we have to find out this integral. Look here, find this. This implies you have integral of 1 to 2, this is r cross d2r by dt square dt will be accordingly r cross dr by dt from t is equal to 1 to t is equal to 2, as you do in definite integral. You have to first give the upper limit and then minus lower limit. It is the fundamental theorem of integral. But here, before going this, we have to find out what is now this. We find out what is r cross dr by dt. We know r is given by this, and we have to find out dr by dt. Then the cross product. For cross product, we will use the determinant rule, and after using it here, we will use the limits. Let us name this equation number 1. We may need it. Equation number 1. You see how we go. Well, I will find out here, differentiate this with respect to t. This implies derivative of r with respect to t will be equal to, it is 10 ti, I is a unit vector, it is j minus 3 t square k. This we have found. Now what is r cross dr by dt? How you find out it? You find it by determinant rule as usual. It is determinant rule is write the first coefficient, this I, j, k, okay. Then components of r. What are components of r? It is 5t square, it is t, then it is minus t cube. These are the components of vector r. Then components of dr by dt as usual. It is 10t, it is here plus 1, coefficient of I, it is minus 3t square. Now let us evaluate this as by determinant rule. What does this give you? It is equal to unit vector I into, delete this row, this column, it is minus 3 t cube plus t cube, delete this and multiply this, plus, then minus j, delete the column and row in which the j lies, it is minus 15 t4 plus 10 t4. Am I doing right? Delete this column, this row, this goes this thing, this column and this row, it is this minus 15, this is plus 10. Yes, it is okay. Then plus k, delete the corresponding column and row in which this lies, k, this and this is deleted, it is 5t square minus 10t square, 5t square minus 10t square. Let us simplify this. What is this now? This is minus 2 t cube I, this is your here minus 5 t4, that will be plus 5 t4 j, plus 5 t4 j, and this is here minus 5 t square k. Okay. I am simplifying this, minus 2 t cube, it is minus 5 t, it is minus here, this will become 5, positive 5, this is minus 5 t square k. Now use this in first equation. Using in equation number 1, when we use it in equation number 1, what we get? We use this result in equation number 1. This gives us integral of 1 to 2 r vector cross d2r by dt square dt is, give this value, minus 2 t cube I, unit vector I, plus 5 t4 j minus 5 t square k. This is from 1 to 2. As usual, give the upper limit, it is the value to t, to be given to t, it is equal to, give the value to t, it is minus 2, when you give the value to this, it is 2 cube, I will just elaborate it, 2 cube I plus 5 or 2 4 j minus 5 2 square k, then minus, give the lower limit now, minus 2, it is 1 cube I plus 5 1 raised power 4 j minus 5 1 square k. Let us simplify this. What is this? We have to simplify this. This will be your, this is 8 into 2, it is minus 16 I, and this is 2 2s are 4 2s are 8 2s are 16, 16 into 5 it is 80t 80j, yes, it is 80j, then this minus 2 2s are 4 4 5s are 10 this 20 this is 20k, then this is minus, this will be your minus 2i, this is plus 5j, this is minus 5k. This we are simplifying. Now we have to connect this with this. This will be your minus 16, this is your plus 2 I, this is plus 80, and this is your minus 5 j, 80 minus 5 j. Okay, this is plus minus 20, this will be plus minus 20 plus 5 k. So the required result of this integral is given by, it is minus 14i plus 75j, then minus 15k. This is the integral 1 to 2 r cross d to r by dt square. You can come across the questions like this, where you are given the vector, you are given a vector point function, this is a vector point function in T, and you are asked to sometimes find out r cross d to r by dt square, or sometimes find out r cross d3 by d, like this. So when you have to find out the cross product, you have to take the help of the determinants. Okay, I will take one more example where I will take here dot. Okay, let me have this, that also I will also discuss that application. I will write one more example, this application here. This application I will do like this. This is the application. A vector point function RT is defined as a vector point function R of t is defined as, I will define it in breakup form, defined as, it is given by R of t is equal to this way, it is 2i minus j plus 2k when t is 2, when your t is 2, it is 4i minus 2j plus 3k, 4i minus 2j plus 3k when t is 3. So this is defined at t is equal to this function, at t is equal to 3, it is 4i minus 2j plus 3k. Suppose you are asked to find out the integral, definite integral, it is 2 to 3 vector integral, it is r dot dr by dt. Well, you have seen in previous question we had cross here, the result that we got is not a scalar, that was again a vector. As you did in previous 8th lecture, I have told you when it will be a vector, integral of a certain vector point function is sometimes a vector or sometimes it is a scalar. Here we are finding out the dot product. It is a integrand, is actually integrand is r dot dr by dt. This is a vector, this is a vector. Dot product of two vectors is again a scalar. So we will see that later on this will be a scalar. You see how we go, we have done this also. What is this equal to dot product? We will go this way. You have this result in previous lecture number 8. There we have found out it is expression, but here I will also do it like this. Solution. We have derivative of vector r square with respect to t. You have seen in r square we have this r dot dr by dt. How? It is derivative of d with respect to t r dot r, because r square we can write r dot r, a square vector we can write a dot a. So this is your dr by dt dot r plus r dot dr by dt. What I am doing? I am applying the derivative of the dot product. Now I need this one. I can write, because this I can write, because you have always that x dot y is equal to y dot x. There is no ambiguity if I write this dr dt dot r as r dot d, so that I will get this twice. This is equal to r dot dr by dt, then this is again plus r dot dr by dt. So what I am getting? This is 2 times r dot dr by dt. Therefore I get derivative of r square with respect to t is this, or I can write this also, derivative of 1 by 2 r square with respect to t is what? It is r dot dr by dt. And what does this imply now? This implies, by definition of the integral, that integral of r dot dr by dt with respect to t is your 1 by 2 r square. Don't add constant of integration here, because we have to find out it from definite integral 2 to 3. We want to find out 2 to 3. Here also we write it from 2 to 3. 2 to 3. You see how we go now. So we have now integral of 2 to 3 r dot dr by dt with respect to t is 1 by 2 we can take out. It is vector r square at t is equal to 3 minus vector r square at t is equal to 2. What I am doing here? I am replacing the upper limit first, then minus lower limit, definite integral. So I have to find out now r square at t is equal to 3 and value of r square at t is equal to 2. Use it here and find out the result. Let me name this equation number something, say it is first equation. You see how I go now. Now let us see what is my r square. It is your r dot r. If I write here at t is equal to 3, at t is equal to 3. So I have to give the value of r to r here, value to r here, that value where r is given for t is equal to 3. You look at the problem that we have discussed with you. At t is equal to 3, r takes the value, it is this value. At t is equal to 3, it is 4i minus 2j, it is from your question, plus 3k, it is the value at t is equal to 3 dot the same 4i minus 2j plus 3k. You see how we do, because we have defined the problem at 2 points. At t is equal to 3 what it is, at t is equal to 2 what it is. I have deliberately tackled this problem. Sometimes you get the problems like this when r is a function of t and r is defined in 2 ways or in 3 ways if you have to find out the more than one definite integral. In any way, I have used the value of r this here because this value of r is defined at t is equal to 3. Let me find out what is this dot product. It is 16. This is plus 4. Quotient of this plus 9. This is your, yes, this is your 29. So you have found r square at t is equal to 3 is what? It is 29. Again we find out r square at t is equal to 3, at t is equal to 2, sorry, r square at it is r dot r again at t is equal to 2. What I use the value of r here? It is another value which is defined in the problem. What is that? That value is when r is 2, my value is 2i, it is 2i minus j plus 2k, 2i minus j plus 2k. It is dot with the same, it is dot with 2i minus j plus 2k. Take the dot, what is it? It is 4 plus 1 plus 4. It is your 9. Using this, if I name this second, this is third, using second and third in first, using second and third in first. Well, when you use here, it is your 1 by 2. What was the value? It was 29. It was minus 9. And this is 1 by 2, 20. It is 10, which is a scalar. So integral of 2 to 3 r dot dr by dt with respect to t is 10. This is how we apply this vector integration in certain problems where we have to find out the integral of cross product, integral of dot product. If it is not the definite integral, it is direct, then you have to add the constant of integration, and that constant of integration, as I have already told you, sometimes it can be a vector independent of t, and sometimes it can be a constant. If the integrand is a vector itself, then the constant of integration will be a vector constant, and if this integrand is a scalar, then this constant of integration is a scalar. In any way, this is some applications I have discussed with you. Next we shall take now line integral. What is line integral? Okay, before we take this line integral, I would like to share with you the students who are pursuing this 5-year integrated course. Some are BSc courses where you have the vector integration, and some are doing the honors course. But for those students, the definitions are very important, definitions as well as application. But the students who are pursuing engineering courses having this vector integration in their syllabus, they have only there the application. You have to touch the application part. That is, what is the application of line integral, how we find out the work done by the force, how we find out the circulation of a fluid, fluid circulation in fluid, and then in that way you will use the line integral. That I will later on give you in this line integral what is the application, physical representation of this line integral. But the definition is very important. You have to read the definition, and engineering students can go for application part. Let me take the line integral. what is a line. I will define this. In simple language, we write here any integral evaluated along a curve will be called line integral. If we evaluate any integral along a curve, that will be called what? Line integral. Now this curve can be open, it can be a straight line, it can be your triangle, it can be a square closed curve, it can be any closed curve, whatever the, sometimes open, sometimes closed, sometimes straight line. If we find the line integral along a curve, you will come to know later on how we find out this line integral. So when we find out along a curve, this will be called the line. Along a surface, then it is a surface integral. You see how we do here. We consider a vector point function, say it is f of p, defined at every point of the curve C and is continuous vector point function at every point of the curve C. It remains a continuous vector point function at every point of the curve C. You see how we go. Let us consider this curve here. I take this a curve. Say this is curve C. This is your curve C from A to B. It is bounded by points A to B. We divide this curve into n parts. Dividing this curve C into n parts, where at P0, P1, P2, say it is Pi minus 1, Pi, Pn. Means this point I take here, this is the division of this curve. At this A, it starts from A. I will take this point as P0. Here I take another point P1, then P2, so on. Say here I take Pi minus 1, this is Pi, and this is your Pn. Means points of division are actually n plus 1. But it gives how many parts? N parts. For this it is very important to, I will write for your reference. Reference is your Riemann integration. How you did Riemann integration? You first take a function fx which is defined, which satisfies some conditions on a closed interval AB. Then we divide the closed interval AB into n n sub intervals. I will give you here reference here. We take fx defined on some interval I is equal to closed interval AB satisfying some conditions. Then we divide it into n subintervals. We take the rth interval here, it is xr minus 1 xr. Then we take delta r, which is xr minus 1. It is the length of this interval, it is the rth interval. If you put r equal to 1, you will get x0 x1, that is x0 is your a, because we start this is your x0, this will be your xn. I am just giving you the reference of your Riemann integration. This is Riemann integration. Riemann integration. In Riemann integration, you find out the lower sums. Lower sums. You find out upper sums. Remember this, lower sums, upper sums. Then you find out lower integral. What is upper integral? And it is those of you who have already done this Riemann integral in previous semesters, please, you will revise this there. Just a definition, what we mean by lower Riemann sum, upper Riemann sum, lower Riemann integral, upper Riemann integral, and then how we define the integral when we say that a function is integrable at point on a closed interval AB. It is when lower Riemann integral coincides with the upper Riemann integral. There also we use for finding out the lower sum and upper sums, we use the limit of sum. We say that lower Riemann integral exists when the limit n tends to infinity, delta r into LP of x when it exists. Similarly, when we find out the upper Riemann integral, there also we use the limit of the sum. It is based on the limit of sum. We take a curve AB, we divide this into n parts by the points P0, P1, P2, so Pi minus 1. Here I take a point here in between this is the arc, we will say it is arc Pi minus 1 Pi. We take here some point Qi. Yes, you will say that this arc is in general, because if I put I is equal to it is I minus 1. If I put I1, it is P0 P1, so I am here, P0 P1. If I put I2, it is P1 P2, I am here, so my Qi will be here, Q2. So what is this? It is a general arc, it is a general section which satisfies all the sections. You can have here, we can have here. So what we define on this section, we take this as a general section on this. So accordingly I write here at every point this, dividing this curve C into n parts, like this, n parts at points P0, P1, P2, Pi minus 1 Pi, Pn. Next we say division is such that so that your P0 is your A, because you start from A, then you have P1, P2, your Pn is the end point of this curve, that is B. These are the n parts of this curve. Then we write let Qi be the point where in the arc which is Pi minus 1 Pi, we take here a point Qi. Then we define as we define in case of Riemann integration, the limit of the sum. Then the limit of sum. Yes, further we need one more thing. We need here one more thing. We write here let R0, R1, R2, Rn. Similarly, have this Rn be position vectors. These are position vectors of points P0, P1, Pi, here you may say Ri, Pn. Means R0 is the position vector of P0, R1 is the position vector of P1, R2 is the position vector of Pi, Ri is the position vector of Pi, and Rn is the position vector of Pn. And you know position vector formula. When we have the position vector of 2 point is given, how we find out AB, vector AB? It is position vector of B minus position vector of A. We are using that here. We take these position vectors and we took here Qi be the point in the arc Pi Qi. Let these be the position vectors of this. Now we define the limit of sum. This is very important. Then the limit of sum, this limit of sum, summation of I running from 1 to n, I running from 1 to n, our function is f qi, this point qi dot delta ri, yes, where delta ri is ri minus 1. It stands for the position vector of Pi, ri minus 1. And absolute value of delta ri tends to 0 when n tends to infinity. This is actually the limit of the sum. If this sum exists, if it is a finite, we find this summation as in case of Riemann integration. We find summation of I running from 1 to n f of qi dot delta ri. What does this stand for? It is delta ri is ri minus 1 position vector formula, and absolute value of delta ri tends to 0 as when n tends to infinity. If this limit of sum is finite, it exists, then it is defined as what? Line integral of f along the curve C. I have already told you we are not here, we are here this is the general point, general section. This general section gives us whole sum from this. It is the sum of these dots. After this I write, if this limit exists means it is a finite. If this limit exists as n tends to infinity. Our language exists means it must be a finite. When we find out this limit, this is limit of this sum, when it is a finite number, then we say, well, then we define that finite this number as the line integral. If this limit exists as n tends to infinity, then we define this means the finite value, this to be a line integral of f along curve C. I will name this sum which I have written here. Let this be denoted by alpha. This sum is alpha. Well, this is usually denoted by is the line integral of f along curve C, which is usually denoted by, it is now line integral denoted by integral of f given vector point function dot dr over C, or sometimes you may denote like this, integral of C f dot dr by dt. This is line integral of f along the curve C. What does this stand for? That limit of the sum, if that limit exists. Well, we have some observations here that you must note. I will write here some remarks or observations. Number one is this, the above line integral, when we take dot product in sum, which I have denoted by alpha, if we take there the scalar product, then this is a scalar. The above line integral is scalar. Remember this in case of dot. Number second, I will use it here. This integral is also called tangential line integral. This will be also called tangential line integral. It has also the name tangential line integral. Third point I will write, if the scalar product in above sum, which is alpha, if the scalar product in above sum alpha is replaced by vector product, then corresponding line integral is integral of C given vector point function, it is cross dr. This will be the line integral. In that case, if we replace there where we have this mentioned summation of I running from 1 to n f of qi dot delta r, if I write there cross, if I need there cross, then this is the line integral, and this here will be a now, what is this, which is vector, which is a vector. It is here now vector. It is corresponding result will be a vector. In some cases, I write this one more point. If vector point function f was our vector point function is replaced by scalar function, if we replace it by some scalar function, then what is corresponding line integral? Then corresponding line integral is, remember this, it is integral over the curve C. This will be phi, which is your scalar function, phi dr. This is your, in that case, here you don't have any dot, you don't have any cross. Remember, when function phi is a scalar, you don't need to take dot, you don't need to take cross. You take dot with the vector, vector dot vector, you take cross with vector dot vector, vector cross vector. When it is a scalar, you simply have phi times dr. You know what has the dr. This we will also when we discuss the working rule, I will there give you how we find out dr. In any way, this what will be now this integral. This is the line integral. In case of a scalar point function, what is this? It will be a vector. It will be a vector. So remember this. When we have a vector point function f, we find out the line integral in the form of integral of f dot dr. That will be a scalar. And if we find out f cross dr, it is also a line integral over the curve C. It will be a vector. if our function f is now a scalar, and we find in that case phi dr, not dot, not cross here, this is also a line integral and it will be a vector. It is something about how we find out line integral, but I have already told you it purely depends upon how we do in case of Riemann integration. We divide the closed interval this into n parts, then we take the rth interval, then we find out their lower sum, upper sum. Here in this case also we find the value of the function at qi. Qi is a point in between the say ith this division this part of the curve. There it is the part of the curve, then we define the sum. If that sum exists when n tends to infinity, then we say is the line integral. The more important thing is now, what is the application, physical application of this line integral, where we apply this line integral. The physical application is very important for the students who are pursuing this engineering courses. They don't have to go these theorems extra, but the students who are doing the undergraduate courses, BSc courses, 5-year integrated courses, they have to follow the definitions, they have to follow the theorems, and those students who are in engineering, they have the application part. I will also discuss next the application part of this, and I will also discuss with you the working rule for finding out this line integral. Very simple, it will be very easy. I hope you have understood this 9th lecture on this vector calculus. Till then you revise, and we will meet next. Thank you very much. Wish you all the best. Take care, my dear students.